A huge thanks to Brian for sponsoring this video. Today, one of the most fun math problems I have solved in quite a while. Try it out for yourself. It's a very, very cool math problem. Here is what it states. Suppose we have a sum of numbers adding up to, in our case 10, we are going to generalize this to a constant thing, something for example 10, 69, 420. Then, what is the maximum value of the product of all the x's? Try it out for yourself. It's an extremely fun problem. We are going to solve this one step by step, and then we are also going to generalize it in the process. I really like this problem. It was so much fun to solve through, and you should try it too. By the way, two things. First things first, this video has been sponsored by the wonderful people over on Brilliant. More information at the end of the video. If you're into mathematics or STEM related things, physics, etc., Brilliant is definitely the perfect website for you. So watch until the end of the video for the solution and also the sponsorship. And also I finally brought out new videos over on Flammy's Wood, my second channel. So if you want to see a completely different side of your Papa Flammy, then please make sure to check out the videos. Links down there in the description. It would mean a lot to me. You can support my channel this way massively. So let us dive right in. So we are going to deal with this original problem, and then in the process we are just going to generalize this a tiny little bit, and the solution is probably going to surprise you. So first things first, it's not stated how many x's we have. So for example, we could have, we are going to do this step by step. We could have the scenario where we have two x's added together. Okay, so we are going to take a look at the first scenario. X plus y, for example, is equal to 10. Now, to get ourselves a maximum product, there are two things needed. On the one hand, we need to know what x and y are. Is there a certain pattern that all of this abides by? We don't know this yet, we will see about it. And the second thing is something that might come as a bit of a surprise, but we'll talk about that later. First things first. How would you find out the product of those two values, x1 and x2 in our case y? Well, you would just multiply those together. So we have a sum given, x plus y is equal to 10. So what exactly is x times y? Now the cool thing with those two variables is that we can just substitute one for the other in. This is just a system of equation. So let us solve, for example, for y in this case. So y is equal to 10 minus x. So if you were to plug this in, we are going to get x times 10 minus x, which is equal to 10x minus x squared. Now what we are going to do is we are going to just, such that you get an understanding for what one of the boundary conditions is going to be for maximizing this product. What we are going to do is we are going to call this part that we have right here as being f of x. We are going to define it as a function. And remember what our goal is. We want to maximize x times y, which is the product of our two variables. So maximizing this product is the same as maximizing this function f of x. So how are you going to maximize it? Well, we are going to take the first derivative. So f prime of x is going to be the same as negative 2x plus 10. And how do you maximize a function? You are going to set the first derivative equal to 0, because maximizing means that we have a maximum in this function, which is going to be the highest point of a parabola in this case. And this parabola there, the derivative is 0. Okay, you are just going to get a constant function over there with a derivative of 0. Meaning we have no slope. So this right here is equal to 0. So what we're going to do is we are going to solve this for x. So adding 2x on both sides, dividing by 2, giving us that x is equal to, in our case, 10 over 2, which is nothing other than 5. Okay, so if x is equal to 5 and x plus y is equal to 10, then 5 plus y is equal to 10, meaning y is also going to be 5. So x and y are going to have the same value. And now you might ask yourself, do we always get the maximum product, the maximum value out, if all of if all of our variables, all of our xi's are equal. And this is indeed the case. You could go through the same process with 3 variables, then parameterize everything, getting a function with respect to x and y out, differentiating both, giving us a system of differential equations, which we are going to maximize in the same matter. You're always going to get out that x and y and z must be the same value. And this can be generalized even more. And for this, I would like to take a look at just all of those x's, for example, adding up to a certain sum. So let our sum, just a constant number, be equal to x1 plus dot 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 up until xn. Now, what you could do here is you have n samples. What you could do is you could divide both sides by n, for example. And what do we get here? This is just the arithmetic mean. And there is a certain inequality, the so-called AMGM inequality, namely that the arithmetic mean is always greater or equal to the nth root of all of those x's multiplied together. This right here is the geometric mean. Now, do you see a relationship here? We have our sum of x's and we have our product of x's. And when is this product maximized? Now, what is the biggest value this product could take? Well, the biggest value that this product could take is if we would get an equals relationship here. The AM is greater or equal to the GM. So the biggest value that this root of the product can take is if we get an equality here. How can you get an equality? Well, you probably guessed it by now. If all of the x's are equal, meaning all xi's are equal to xj, meaning what we are going to get if xi is equal to xj, meaning all of those are equal to x, we are going to get that x plus x plus x blah 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 n times is going to be n times x divided by n, which is nothing other than x, is, and now we are going to get the right hand side, we are going to get x times x times x n times, so we are going to get the nth root of x to the nth power. The root and the power is going to cancel out, giving us an equality in the process. And this right here is the generalized case for what we have observed here. So one condition for maximizing our product given a certain sum of those samples is if all of those x's are completely equal. Now, you might say, okay, now we have found the key to this whole thing. So we probably solved this problem right here. Well, there is one more variable that we need to take into account, and it's a bit counterintuitive, but if you think about it and go through a few cases right here, you are going to notice that the number of samples actually matters in this case. So let us take a look at the number of samples being equal to 2. So n is equal to 2. Then what we are going to get is that our product x times y is going to be 5 times 5 is 25. Okay, so we have found this out. So for a sample size of n equal to 2, we are going to get that x times y is equal to 25, which is 5 squared. Now what about n being equal to 3? Now think about it. We have 3 samples now and all of those are equal. So we are going to get x plus x, so 3x is equal to 10. Now dividing both sides by 3 gives us that the value for x is equal to 10 divided by 3. Now we have 3 samples, meaning we are gonna multiply our 3 samples together. So this gives us x times x, which is x cubed, and x is 10 over 3, which is going to be 10 cubed, which is 1000, divided by 3 cubed, which is 27. And this gives us roughly, I would say 40, but we need to be a bit careful about that. This is roughly 37. So if we have 2 samples, we get 25, and if we have 3 samples, we get 37 out. Now, let us continue this process a bit more. What about n being equal to 4? Then you might guess it, we get 4x is equal to 10, meaning overall that x is equal to 10 divided by 4. Meaning overall we have 4 x's being multiplied together, so x to the 4th power is equal to, okay, this times 10 is going to give us 10k. divided by, and 4 to the 4th power is the same as 2 to the 8th power, which is 256, which is seriously roughly 40, and to be a bit more precise, it's roughly 39. Those two are very close together. Now what about n being equal to 5, for example? Now we are going to get 5x is equal to 10, meaning x is overall equal to 2, meaning x to the 5th power is going to be 2 to the 5th power, which is going to be 32. Now I have spoiled our original problem a tiny little bit, and you can tell me down there in the comments if you have found the solution, that this very product right here is going to be maximized if we have 4 samples overall, where each and every x is going to be the same as 2.5. Then we have a maximized product of around 39, which is pretty close to the case n being equal to 3. Now this was the solution to the original problem, but we can go further, and we can now generalize this a tiny bit more, because this right here is an interesting relationship. I mean, when I first looked at this problem, I thought that I would be done at this point, but then I noticed, well, the sample size does matter. How many samples do we have? And this is why we are going to take a look at the generalized case now, where we are going to have n samples, and then we are going to maximize this function with respect to the samples to see when is our product maximized, in which way, when we have a certain number of samples. So for which number of samples is our product always going to be maximized? This is what I wanted to say. So let us go through this process step by step. So the first thing we are going to do is we are going to say that all of those x's are going to add up to a sum s once again, okay? So this problem is done, the original problem is done. Now we are going to go generalize this whole thing, just like we do it here on this channel a lot of times. Now x1 plus dot 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 up until xn is going to be a sum s, a constant. Now this constant right here is going to be reached or maximized overall, or the product overall, if all of the x's are equal. So once again we are going to go a step further, and we say that n times x is going to be s, meaning x is going to take the value, just like we have found out before, of being s divided by n. Now we are going to take the product of all the x's multiplied together. Now remember, we are going to get n x's overall being multiplied together. So our product of x1 times blah 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 up until xn is going to be the same as x to the nth power, which is x is s divided by n, s divided by n to the nth power. And this function right here with respect to n is what we're gonna maximize now, because we want to see for which n, for which sample size, is our product maximized overall. So we are going to call this f of n. N, please note, is going to be an integer, a positive integer after we are done. But for now we are going to treat n as an element of the real numbers. So this right here is what we want to maximize. And once again, we are just going to take the derivative. And to take the derivative of an exponential function, we are going to turn this into something e to the logarithm. So s divided by n to the nth power is the same as e to the natural log of s divided by n to the nth power. So this is the first thing we are going to do. So f of n is the same as e to the natural log of s divided by n to the nth power. Now the nth power we can bring to the front. I'm going to do this real quick. So we're just going to get rid of that. N times the log of s divided by n, and the natural log of s divided by n is the natural log of s minus the natural log of n. So this is going to be now the function e to the n times log of s minus n times log of n. It does look complicated right now, but it's now way easier to differentiate. Let us differentiate all of this. So what is going to be f prime of n? Now, after differentiating all of this, our original function is going to be preserved. It's going to be this exponential function, s divided by n to the nth power. This is just the outer derivative, but what about the inner derivative? The inner derivative is the derivative of this whole thing. Now the derivative of n times log of s is just log of s, obviously. So the natural log of s. Now we got negative, the derivative of n times natural log of n. Now we have to use the product rule for this. At first we are going to differentiate with respect to this first n here. This is going to turn to the constant 1. So negative log of n. And last but not least, the second part, we are going to differentiate log of n with respect to n, which is going to be 1 over n. And 1 over n times n is going to be 1, or in this case negative 1. And this right here, we want to maximize it, must be equal to 0, and overall this value must also be positive if we take the second derivative, for example. No, it must be negative because we have a high point. Okay, this is also something you would need to check in normal case, but I didn't do that here because it's rather obvious. Now, when is this derivative equal to 0? It's a product of two things, and the exponential function for no value of n is ever gonna approach 0. Meaning, this part right here, which is in brackets, must be equal to 0. This is the only logical consequence. So log of s minus 1 minus log of n must be equal to 0. And now we are going to solve this whole thing for n, because we want to see when it's maximized for that value. Now we are going to add log of n on both sides, giving us that log of n is equal to log of s minus 1. And the cool thing is, 1 is nothing other than the natural log of e. So we can actually play around with this expression a bit. So log of n is the same as log of s minus log of e. And by logarithm properties, log of s minus log of e is log of s divided by e. And since the logarithm function is increasing, we can just take the exponential function on both sides. The inverse function giving us that n is nothing other than s divided by e. So our product is going to be maximized if all of our x's are equal and if our integer n is going to be the same as our value of the sum divided by e. For some reason, Euler's number e plays a role in maximizing this very problem. Do you notice something? This was just a regular number theory problem, but we have turned this into a matter of analytic number theory, which is outright beautiful. Now, think about that a tiny little bit. S divided by e is most certainly going to be an irrational or let be transcendental number. I don't want to prove this here. I don't even know if this has been proven before, if the reciprocal of e is equal to a transcendental number or an irrational number. Really doesn't matter for now, but you have to round this up or down, obviously, to the closest integer, because we have a sample size here. Okay, so n must be a positive integer. But for that, our n or our product is going to be maximized for this value of n. For example, n being equal to 10 divided by e maximizes as the sample size our original problem. 10 divided by e is 10 divided by 2.5 roughly, which is going to be 4. And you guessed it, for n being equal to 4, this bit was indeed maximized. Isn't that absolutely cool? And then you can plug the value for n into our x, which is here, meaning our product, or x to the n, is going to be the same as s divided by n. So s divided by s divided by e is going to be e to the s divided by e. And this is going to be the value of the product overall. And this is the generalized solution to this problem. And I hope you did enjoy what you have seen today, and maybe you were able to figure out at least the original problem and maybe also the generalized solution out. And if you did enjoy what you have seen today, if you are into number theory or let alone analytic number theory, calculus and all this crazy stuff that you can find in the realm of mathematics, then Brilliant might be the perfect fit for you. Oh man, here we go again, exponential function popping up. We suddenly turned this summation and product stuff into this analytic number theory fest where we suddenly started maximizing a function. It's absolutely ridiculous. And do you know what the cool thing about problem like this is? You could also theoretically solve this graphically by plotting all of the axes in a coordinate system, or maybe even this function that we have defined here, and then you could try to find the value for n such that all of this is maximized. And solving problems like this graphically could be beneficial for a lot of people because not everyone is into abstract mathematics and all those things that we have written out here. Many people just don't know how they could deal with problems like this in such a way. So what they like to do is draw a graph of a function and see if they can interpret something like this in a visual kind of way. And this is exactly what Brilliant is for. If you are a visual learner, someone who just loves to touch things and try around with their own two hands to see how they can solve problems in an alternative fashion, this is what Brilliant is all about. And I could tell you for hours how cool the contents of their website are, but you should just see for yourself how their course concept works. Now, Brilliant is your source for some of the best online learning content that you can find out there on the World Wide Web. It's just absolutely fabulous, and doesn't matter what you're looking for, be it mathematics content, new things to learn in physics, chemistry, computer science. Really doesn't matter what it is in the STEM field. Brilliant definitely got one or another course for something that you want to learn right now over on their website. And as mentioned before, their course concept is a one of a kind. Not only do you learn something new from scratch, be it group theory for example, you start off with a bunch of definitions and just an introduction, but then suddenly it starts to get a tiny little bit harder. But it's not in the way that you see it in class, for example, with all those formulas being put on a chalkboard. No, it's a bit different over on Brilliant. They give you those abstract formulations, but also little pictures and visuals right next to it. And including something like this into a learning environment is very beneficial for a lot of users. And for the people who subscribe to Brilliant through my channel or other means, I only heard great feedback from them because they were able to learn something new in a rather short amount of time with a totally different understanding that I do, for example, in a normal case when I grab a book or lecture notes and just try to learn something about a new topic that I have never heard something of before. But as mentioned before, I could tell you hours about Brilliant and how cool it is and what you can do over there. But the best way to experience Brilliant for yourself is by just trying it out. And the best thing is you can try it out for totally free for 30 days if you use my link at the top of the description, brilliant.org/flammable. As mentioned before, 30-day free trial. Just try everything out to your heart's content. And if you think this could turn into a long-term relationship between you and also Brilliant, then you can seriously make clicky on the linky down there and get 20% off an annual premium subscription, which is a fantastic deal considering how much content they already have available on their website and how much content they are putting out on a regular basis. So you should most definitely check it out and try to learn something new every day for the next few weeks, months, whatever. However you choose, do it. And it's seriously going to benefit your studies in some kind of way. And I thank you guys for watching. And if you did enjoy this video, then make sure to subscribe to the channel. And I really loved this problem. It was so much fun to solve for myself, and I hope you had fun too. Don't forget to also subscribe to my other channel, Flammy's Wood. And up until next video, I wish you guys a very fabulous day. See ya.